Bismillahirrahmanirrahim. In this lecture we will discuss equilibrium conditions, and with the help of these conditions we will see that our stress tensor is symmetric. Then we will derive relation between stress and strain, which is called generalized Hooke's law. After that we will see the matrix form of stress strain equation. Let us start from the equilibrium conditions. Basically we have two types of forces. One is surface and other is body force. Surface force means that surface force is that which has a contact with the object. That when you apply the force on an object, then you have a contact with that object. That is called a surface force. And body force, when body force acts on an object, then that force has no contact with object. For example, gravity. Now if these two forces are acting on a continuum, then that continuum is in state of equilibrium if we have these two conditions, which are called equilibrium conditions. First one is sum of forces equal to 0. Sum of forces means total surface force plus body force equals to 0. Then the sum of movements about any point, basically torques produced due to these two forces equals to 0. Sum of torques produced by these two forces equals to 0. This is the first condition, that this is the total surface force and surface integral, and this is the body force, total net body force. This is basically ith component of total force. This is basically the ith component. You can see that K is dummy and I is free. Here I is also free. So this is the ith component of the total force. Our movements about origin, torques. This is torque. F is force, then R plus F is the torque. This is the ith component. Torque is basically vector, so ith component of torque we can write in this way: epsilon ijk rj fk. I will be balanced with this ith component. Now we will use this definition here and here. Here we have epsilon ijk instead of r, where we are using xj, the coordinates x1, x2 and x3. No, for r we have x, and for f here we have tik lk. Now this will be epsilon ijk here, epsilon ijk rj xj, then fk. Here we have this f, so it will be tk. Now we have to change this dummy index qq. We cannot write k 4 times, so we will change this by q plus rho x epsilon ijk xj rho as it is fk. Simple. This is simple. Here instead of f we have small f, so fk xj fk. This is equation number 2. Now in our previous lecture we have studied the Gauss's theorem. We have written the statement of Gauss's theorem, that what is the use of Gauss theorem. Here in equation 1 and equation 2 we can see that in one term we have surface integral, and in second we have volume, so we have to make these two integrals same. So we will use the Gauss's theorem and change this surface integral into volume integral. So if you remember, this is simply Tik second order, this is Lk, it would be Tik comma k, this is kk dummy, Tik comma k, and dv simple plus this is as it is. So we can write this as, and we know that we are dealing with an volume which is arbitrary, and this is continuous. These are forces and we are considering the continuous continuity. From the start we have supposed that everything is continuous, so this would be equal to 0. This is arbitrary and this is continuous, so integral is 0, so integrand will be equal to 0. So from the help of first equilibrium condition we have this type of result, equation number 3. Now we will see that what we have from the second condition. Again we will make the use of Gauss theorem on first term, and we will convert this surface integral into volume integral. So how we can do that? We have this type of here again, instead here we have Tik and here we have this epsilon ijk xj tkq, and instead of here we have Lk, here we have Lq. What is dummy? Q is dummy, K is dummy with this, J is dummy with this. So what would be the result? Simply volume integral derivative with respect to xq, derivative of whole this, derivative of this with respect to simply x q. Different dv plus this. Now we will take the derivative of this. We know that this is constant, epsilon ijk partial xj partial xq tkq plus epsilon ijk xj as it is partial tkq partial xq. What is this? This is delta jq. This is simply delta jq, and this is tkq plus epsilon jk xj, and we can write this tkq comma q, delta jq. No, we know that delta, this is the product of delta with this t, and what is q is dummy here, q is dummy here, so we can write tkj plus this as it is. Put this here and separate the volume integral. For first term we have this volume integral plus we have we are combining this term with this epsilon ijk xj, epsilon ijk xj common, and in parenthesis we have tkq comma q plus rho fk dv. And we know that from the first condition, result of first condition, which is given by equation number 3, this is 0, so this will be equals to 0, so we are left with only this term equals to 0, and we know that our volume is arbitrary, so this integrand will be equal to 0. Here we can see that j and k, they are dummy and I is free. So when I is 1, we have this open summation k and j, we have this it is giving us t23 equals to t32. When I is 2, it will give us T13 equals to T31. When I is 3, it will give us T12 equals to T21. From here we can see that off diagonals are same. T23 equals to T32, T13 equals to T31, T12 equals to T21. In general, we can write Tij equals to Tji for all I and j. For all I and j. Obviously, T11 is equal to T11, T22 is equal to T22, T33 equals to T33. So this is telling us that stress is symmetric tensor. So we have shown that with the help of equilibrium condition, stress tensor is symmetric as strain tensor, which is also symmetric. No relation between stress and strain. Stress and strain. To derive this relation, we shall suppose that we shall keep in mind that deformation is very small. This supposition is from our start, that we will deal with only infinitesimal deformation, and also assume that stress is a function of strain only, that we will take stress as a function of strain. And we know that we know that when stress is 0 for undeformed state, that when there is no strain, it means that there is no stress. So this is written here with the assumption that stress is 0 for undeformed state. We can write this is with the help of Taylor series. At x equal to 0, x means that we are taking the center of that series equals to center is 0. This is Tij as a function of strain. SKL equals to Tij at 0 plus its derivative with respect to SKL at SKL 0 here SKL h plus second partial derivative. It should be 2 divided by 2 factorial. SKL equals 0, SMN equals 0, and h square. SKL and SMN. As we are dealing with infinitesimal deformation, and this for undeformed state. One thing is that we are dealing with infinitesimal deformation, and second thing is that this is 0. Why this is 0? That this is for undeformed state. This 0 is telling that we are talking about undeformed state, and when we have undeformed state, so it means that stress must be 0. This is why we have written Tij at 0 equal to 0. And for infinitesimal deformation, we will retain only first two terms. Other terms which are product of strain tensor components will be 0, will be very small, and they will be neglected in comparison with first order. So we have thisCijkl SKL. Now what isCijkl? This Kijkl simply is equal to this thing which is written here, partial Tij partial SKL at SKL equal to 0. This is Kijkl. Tij SKL Kijkl. Now we have this equation Tij equals to Kijkl SKL. This is the relation between stress and strain, and this is called generalized law, and this is a linear relation between stress and strain. This C is linearly related T and S, stress and strain. You can see that every component of T of stress can be written as the linear you can say linear combination of all components of strain. What does this mean? This means that if you have T11, it will be equal to C11 KL SKL, and you know that we have 9 pairs for SKL, so every strain components will be involved. That for each stress component you have every component of strain on right hand side, in linear form. Linear form means that you can see that power of S is 1. This is second order tensor, this is second order tensor, and this is fourth order tensor. If you remember, you have already proved this thing, that if this is second, this must be fourth order tensor. This we know that these are the components of second order tensor, and that tensor is called stress tensor. These are the components of second order tensor, and that tensor is called strain tensor. Now these are the components fourth order tensor, and it is called elasticity tensor or stiffness tensor. This is called elasticity or stiffness tensor. Now as it has order 4, so its component will be 81. Total number of components will be 81. Now we will see that how many are independent. We know that Dij equal to Ci j KL SKL. Here let us change I and j with each other. Tji equals to Cji KL SKL. This is second equation. And we know that Tij equals to Tji. Stress is symmetric. So from 1 and 2 you can write this equals to this. Using this relation you have 54 independent components. And also we know that strain is symmetric. That means SKL equals to SLK. You can write, you have this equation, and you can write by changing K and L, LK and LK. Now from 3 and 4, left hand side is same. This is equal to this with the help of this, that we are taking that we know that strain is symmetric. SoCijkl equals toCijlk. Now we have 36 independent components. Now what you have to do, you have to find those 36 independent components with the help of conditions A and B. What are those components? Two index notation. Now we will define two index notation, and with the help of this two index notation we will write stress strain equation, generalized Hooke's law. This stress strain equation, stress strain relation in matrix form. When we will define two index notation. Let us define two index notation. We will denote 1 1 by 1, 2 2 by 2, 3 3 by 3, 2 3 3 2 by 4, 1 3 3 1 by 5, 1 2 2 1 by 1 by 6. We are writing this M. In general we can write this M is equal to I when I is equal to 2, then J. 1 equals to 1, M is equal to 1, 2 equals to 2, M is equal to 3 equals to 3, M is equal to 3. And not equal to, when I is not equal to J, we have this M is equal to 9 minus I plus J. For example, 1 and 3, I is 1 and J is 3, 1 3. So it would be 9 minus 4, 5. You can see that 1 3 or 3 1, we are denoting that by 5. C1 2 1 3 in 2 index notation. This is 4 index notation, that 1 2 1 3. In 2 index notation we can write this 1 2 is 6 and this 1 3 is 5. So C 6 5. In this way we can replaceCijkl by Cmn, which can be written in the matrix form as this is in 4 indices and this is 2 indices, 2 index notation. It's 4 indices where mn varies from 1 2 3 4 5 6, and in matrix form then we can write in matrix form. When you have 2 index notation, then you can write this elasticity tensor in matrix form simply: C11, C12, C13, C14, C15, C16. C11, C12, C13, C14, C15, C16. Similarly, second row, third row, fourth row, fifth row, and sixth row. This is called elasticity matrix for elasticity tensor. Now we have this equation, stress strain equation. We will see that how we can write this stress strain equation in matrix form. We have basically 6 components for stress. They are T11, T22, T33, T12, T13, T23. Other three depend on these 3. Other 3 diagonal components depend on these 3 diagonal components. T11 equals to C11 KL SKL. Let us vary K and L. 1 1 1 1 2 2 2 2 plus C11 3 3 S3 3 plus C11 1 2 S1 2 and C11 2 1 S2 1. So we can write 2 times C11 1 2 S1 2. Why? Because we know that C11 1 2 equals to C11 2 1 and C12 equals to C21, so they will be 2 times. Similarly, 2 times C11 1 3 S1 3 plus 2 times C11 2 3 S2 3. We can write this in 2 index: C11 S1 1 plus C12 S2 2 plus C13 S3 3 and plus 2 C14. This is S2 3. 2 C1 and 2 3 4 C14 plus this is 2 C111 and 135 S13 plus this 2 C111 and 126 and S12. Similarly, you have to write T22, T33, then T23, T13 and T12, because T23 is 4, this is 5 and this is 6. So by combining all these 6 equations, we can write those in this matrix form: T11, T22, T33, T23, T13, T12. And this is matrix C, elasticity matrix. This is in strain column, strain components column vector. S11, S22, S33 plus 2 times S23, 2 times S13, 2 times 2S1. You can have first equation T1 equals to C11 S11 plus C12 S22 plus C13 S33 plus C14, 2 times C14 S23 plus 2 times C15 S13 plus 2 times C16 S12. This is the matrix form of stress strain equation or generalized Hooke's law. Thank you so much. We will discuss this tomorrow, inshallah. Allah Hafiz.